Hello, this is Mr. Smith with a video for reading quiz number 1, which is all about how to use algebra to evaluate limits of indeterminate form. What is covered in this PowerPoint? The focus of this particular PowerPoint is on how to use algebra techniques to evaluate limits of indeterminate form. I won't go through every example that's in the reading. And for your current purposes, the limits that we're going to look at of indeterminate form are limits of the form 0 over 0. I won't go into much detail about the limit laws that were discussed at the beginning of this reading quiz. We'll talk about those a little bit more at the start of class. Before we move on, just a word of caution about trying to find limits. When you're trying to evaluate a limit, always try plugging in first, especially if you're dealing with polynomials, rational functions as long as the denominator is not 0, exponentials or other functions that have no breaks. In other words, functions that are called continuous functions, which is a term we talk about later in the unit. In these cases, when you've got functions that have no breaks, the limit is just the function value, and you can easily obtain the limit value by just plugging in the x value into the function. For example, take the rational function x squared plus 1 over x plus 2. In this case, this is a rational function with a problem only at x is equal to -2. So if we wanted to find the limit as x goes to 1 of this function, the limit as x goes to 1 of x squared plus 1 over x plus 2, all we need to do is plug in the x value and evaluate the function at x is equal to 1. When we do so, we get the value of 2/3. Be very careful. We're going to talk a lot about different techniques that are algebra related that we can use to evaluate limits, and not all those techniques are necessary. Sometimes you can just plug in to get your limit value right away. The first technique I'll cover in this PowerPoint is how to factor and then cancel. This is a technique that's particularly useful if we're dealing with rational functions. So if you get a situation where the numerator and denominator are both equal to 0, which is what's called indeterminate form, try one of the following techniques. Factor and then cancel. Once you cancel, then try plugging in again. And remember that when you learned about synthetic division in earlier courses, that is a technique that is used to factor. And it's especially useful if you already know one of the factors, like you do when you have indeterminate form, and we'll see that in just a second. Here's an example from the reading. In the limit below, when we plug 2 into the numerator and denominator, we're going to get 0 in both cases, and I'll let you pause the video if you're not convinced, and you can see that that's the case. This tells us that 2 is a root of both the numerator and the denominator, and particularly t minus 2 is a factor of both the numerator and denominator. Now we've got a situation where we've got cubic functions, and cubic functions it's not always easy to see how to factor. But we've got a hint. We've got a hint in the fact that we know that t minus 2 should be a factor of our numerator because we know that we got a 0 when we plugged in 2 into our numerator. So, by synthetic division, we can factor our numerator. Remember that we are going to put the coefficients of each of our terms of the polynomial in the numerator along the top row. When we work this out, we find out that we get a 1, 5, and a -2, and a 0, which indicates that 2 was in fact a root of our numerator. Remember the 1, 5, and -2 serve as the coefficients for our depressed polynomial. In other words, the t cubed plus 3t squared minus 12t plus 4 factors into t squared plus 5t minus 2 times t minus 2. Similarly, and probably a little bit easier, the denominator factors into t times t minus 2 times t plus 2. Notice both the numerator and denominator have a factor of t minus 2, which is a good thing. Because we had indeterminate form, we should have gotten a 0 over 0 on the top and the bottom, which is what we get when we plug in 2. When we cancel, we're left with the limit as t goes to 2 of t squared plus 5t minus 2 over t times t plus 2. And now when we plug in 2, just like we did in the previous example, we get something that's not indeterminate form anymore. We've canceled out the problem. In this case, we're left with 12 over 8, which reduces down to 3/2, which is the value of the limit. A second technique which you might find useful is your basic function knowledge can help you figure out what a limit value is. Particularly if you know what the graph of the equation looks like, use that knowledge to determine the limit. So take, for example, the limit as x goes to -4 from the right of 1 over x squared minus 16. Remember, we talked about what the little plus means to the right of the -4. It means we're going a little bit to the right on the number line of -4. When we factor our denominator, we are left with the limit as x goes to -4 from the right of 1 over x minus 4 times x plus 4. This is a rational function that's going to have some sort of a vertical asymptote at -4. So when we try to plug in -4, we notice that we get a -8 with the first factor and a number that's a little bit above 0. What I indicate there as a positive 0. So the problem asks us to find out what the function looks like to the right of -4, taking, for example, a number like -3.99. So if we mentally test -3.99 in that factor x plus 4, we find that we get a number that's very close to 0 but is still positive. So that's why I write a positive 0 there. When we have a non-zero number in the numerator and 0 in the denominator, the limit approaches either positive or negative infinity depending on the signs overall of the numerator and denominator. So notice we have a positive number on the top and we get a negative number overall when we look at that total product on the bottom, but it's a negative number that's close to 0. So positive on the top, negative product close to 0 on the bottom, so the limit approaches negative infinity. When dealing with piecewise functions that are composed of functions without breaks, what you need to do is find the correct piece. For example, if we want to find the limit to the left of 0, use the piece just to the left of the 0, and plug in the value, if we're dealing with functions that do not have breaks. For example, if f of x is equal to 4 plus 2x when x is less than or equal to 0, negative 5x squared when x is between 0 and 2, and negative 20 when x is bigger than or equal to 2, and wanted to find the limit as x goes to 0 from the left of f of x, the piece we would look at would be the 4 plus 2x piece. Okay, because that's the piece when x is less than or equal to 0. When we plug in 0, this is just a linear function, which is continuous and has no breaks. We get a limit value of 4. If we wanted to evaluate the limit as x goes to the right of 0 of f of x, we use the piece that's between 0 and 2. Anything a little bit bigger than 0, but not too far above 0, which is the negative 5x squared piece. When we plug in 0, this is just a quadratic function whose limit equals the function value at every possible x value. We get a limit of 0. Now you'll notice that the left side limit does not match the right side limit, so the overall limit as x goes to 0 of f of x, does not exist, or DNE, because those left and right side limits do not match. A fourth technique, you can rationalize by multiplying and dividing by a conjugate. So for example, you had the limit as x goes to 4 of square root of x minus 2 over x minus 4. Now you notice that if you plug in 4, you're going to get 0 over 0, which as we know is called indeterminate form. So our trick here is, in order to get rid of the 0 over 0 portion, we're going to multiply and divide by the conjugate of our numerator, the part that involves the square root. When we do that, we're going to multiply and divide by square root of x plus 2 on the top and the bottom. The top will FOIL out to be x minus 4. The bottom I'm going to leave alone as x minus 4 times square root of x plus 2. The reason I did that is because these x minus 4 portions cancel out. That's a good thing, because that's the indeterminate. That was the part that was giving us indeterminate form, because it was giving us the 0 over 0. So we're left with limit as x goes to 4 of 1 over square root of x plus 2. Now we try plugging in 4. It works. We get a limit value of 1/4. The whole idea again is to eliminate what is giving us the indeterminate form. In this case, there was a hidden factor of x minus 4, which was giving us problems. That's how we knew to multiply and divide by the conjugate, because that gave us a factor on the top of an x minus 4. That could then be canceled. Technique 5. FOIL in order to cancel. Sometimes you got to make things a little more complicated in order to actually get things to cancel out. For example, limit as h goes to 0 of x plus h squared minus x squared over h. If you were to distribute and FOIL the x plus h squared portion, you get a limit as h goes to 0 of x squared plus 2xh plus h squared minus x squared, and notice that the x squared portions will cancel out. When you cancel that out, you get limit as h goes to 0 of 2xh plus h squared. Then you can factor out an h from the top and cancel it from the bottom, leaving you with the limit as h goes to 0 of 2x plus h. The whole big point of that is, because we were able to cancel out an h from the top, after we expanded, then we were able to cancel out what gave us indeterminate form. Now we've got a situation where we can just plug in h equal to 0 and we get 2x as our limit value. This will be a limit that we see quite often. In fact, what we just did was found the derivative of the function x squared. Technique 6. Simplify fractions. This one gives students problems from time to time. So a technique that you can use is try to simplify fractions by finding common denominators, then cancel, and then plug in. So for example, if you had limit as x goes to 0 of 1 over 2 plus x minus 1/2 over x. Notice you've got a really complicated looking function and two fractions on your numerator. So the trick is to try to find a common denominator. In this case, the common denominator will be 2 times 2 plus x. When we work with our numerators of our fractions to try to fix that, we get 2 minus parentheses 2 plus x over 2 times 2 plus x in our new numerator. Notice that I kept parentheses around my 2 plus x part because there's a negative here. That's one of the main problems that students have, getting their parentheses. We also have an x in our denominator, which I'm going to rewrite right here as 1 over x. Okay, when we simplify in our numerator, we end up with negative x, and that's all over 2 times 2 plus x, and then multiply by that 1 over x that I just mentioned as the limit of x goes to 0. Good thing, the x's cancel out. That's the part that's giving us our indeterminate form. When we cancel, we get limit as x goes to 0 of negative 1 over 2 times 2 plus x. Hey, look at there, we can now try to plug in 0, and we get negative 1/4. In the second step, remember we found a common denominator for our numerator's fraction. Don't forget that negative sign, it's important. Finally, again, knowing what a function looks like can help you figure out what a limit is. For example, from number 20 of the reading quiz, if you wanted to evaluate limit as x goes to pi over 2 from the right of tangent of x, we can take a look at what the graph of tangent of x looks like. In this case, pi over 2 is right here, which is where one of the first vertical asymptotes is for tangent. If we're going to the right of pi over 2, look at what happens to tangent. It has approached negative infinity and is in fact coming back up towards 0. So what we would say is the limit as x goes to pi over 2 from the right of tangent of x would be negative infinity. If we looked from the left of pi over 2, that limit would be positive infinity.